Wow, what a great morning of great talks. That's it for me on this stage, but you still have a full afternoon of S-tier speakers. My name is Jane Harrell. I'm from Covalent. You can find me on Twitter and Telegram. Next up, we have Zisk, zkProving in real time with Jordi, Baylina from Polygon.
Hello, everybody. I'm Jordi Baylina, co-founder of Polygon, and I want to present today Zisk. Zisk is a common good. It's an open source project, and mainly it's software. It's zkVM 64-bit RISC-V proving system. Okay, it's a system that's very much optimized for generating, for proving in real time. It's using, the idea is that you can write any program in Rust, and you can write circuits in Rust, and then you compile and you generate that. The difference, the big advantage of, well, you can try it here. It's fully available right now. Still some audits and some improvements that still in the backlog, a lot of things to do, but right now it's fully working, it's fully proving. You can write a Rust program, and it already proves, and you can try it here. Anybody that wants to, have any doubts, please don't hesitate to contact us. Okay. As I was telling, the main goal of Zisk is minimize the latency, being able to build proofs as fast as you can. Here, we may sacrifice a little bit of the price of the cost. The costs are already very low. And what we want to do is generate proofs fast. Ideally, and we will see how we can do it, ideally, for example, to prove blocks, Ethereum blocks, or rollups blocks in real time. Why is this important? Well, that's important, for example, for when you have many rollups and you want to transfer funds from one to the other, when you have two chains that are not that you don't really, one of the chains can be malicious. In order for one chain to be sure that can use the funds of the other chain, well, you need that the other chain is committed, so that the other chain is final, that cannot go back, and needs also to check that the other chain is correct. You can do that in two ways. You can do that by following the other chain, maybe spinning up some servers and following the other chain, but this does not scale well. If you have a lot of chains, it's not practical to spinning up servers every time that a new chain is created or a new chain is moved. Okay, so the way is that each chain generates a proof that validates the correctness of that state, and then the other chains can just use that proof in order to validate the chain without having to spin up all the chains. That's why it's important, this tech, for aggregating in the aggregation layer, for aggregating different rollups. It's also important to mention, for example, that in the Bean chain in Ethereum, everything is based on these proving blocks really fast and doing a lot of proof on that. So all the consensus that they are building on there, so it's important to have this technology in place. Okay. Zisk is, well, it's a little bit more that that's this zkVM. Actually, this zkVM is built on top of a proving system, a full proving system. This proving system has a full language. It's a language for arithmetization. And it's a proving system that can be used for any prover. For build up zkVM, but can be used also to build other processors. This is very much using all the technology that we already developed inside Polygon, with inside Hermes and Plonky 2 and Plonky 3. So all the knowledge, all the know-how is already there. All the security, knowledge, the bug bounties, having that in production. All the learnings and all the knowledge is inside this product. Okay? And on top of that, there is also a small piece, that's the recursor, that allows you also to aggregate proofs on that in a simple way. Peer-to language, I'm not going to extend to that, but it's it has been, in the zkVM, we use it PIL. This gave us a very good result. So PIL2 is an extension on that. And it allows very much to support what we call the VATCOPs. Okay, the idea of the VATCOPs is that instead of having a huge monolithic proof, as we had, for example, in the zkVM, the idea is that we can split this proof in small subproofs, I mean, in small pieces. Okay, this allows us to scale horizontally, so we can send all of these pieces, all these state machines in different servers. We can configure the size of these pieces, so we can have a decentralized system where each part is building one of these parts of the servers, and then with the recursion technology, we aggregate all them together in order to build a single proof. And I mean, all the design architecture of Zisk is on that. I mean, it's trying to decentralize, I mean, trying to split the work as much as you can. Okay, we will see then in the last slide how we split the timings on this slide. Okay. Well, I'm not going to extend, but the proving system is very much you write this arithmetization and you write the witness computation. And with all that, that's the only thing you need to build. With all that, you have a full proving system that can work in a single machine or can work in a service. Okay. I'm going to jump this little fast. Zisk, I mean, when you're building a Zisk, what you do? Well, mainly this is the workflow you do. You just write a program in Rust. You compile in Rust using RISC-V 64 bits, so you generate an ELF, okay? And then with this ELF, you just send it to the prover together with an input. I mean, generally some input file. You want to prove something, okay? So you have a program and you have an input that some data that you want to process, okay? And the prover will generate just the proof and the public input that you can verify, okay? The program also you can hash it so that the verification you are sure that you are verifying against exactly this exact program. So it's as simple as creating a normal Rust program. The internal. So one of the key technologies, as I told you, is this division of the pieces, okay? The most important, I mean, and the idea is that all these pieces, they communicate to each other, what we call a kind of a bus, okay? A kind of a bus, very much what it says is, for example, in the main processor, you are, instead of, you may do, for example, a multiplication or a division, or you're doing some operations. Okay, so instead of doing the operations in the main processor, what you do is in the main processor, mainly what you do is you assume that this multiplication is correct without proving it. Okay, and then we add that to the bus. And in another state machine, in another piece, that's more specialized state machine, for example, in arithmetic, you just take and you prove that concrete multiplication or division or addition, okay? And then you subtract from the bus. So the idea at the end is that when you have different state machines, you sum up all these buses. These sums is with some random number so that you cannot, you cannot trick it. And the idea is at the end, all the sums needs to be 0. So everything that's assumed for some state machine is somehow proven in the other state machine. So this allows us, for example, to do some interesting things like this. For example, in this, you have some operations. For example, you have a multiplication, and you will have, for example, an arithmetic that will subtract from the bus. So in the processor, we'll add, and the arithmetic subtract. But if it's an arithmetic, for example, that's a very common arithmetic. For example, it's 1 times 1 or 2 plus 2. Instead of using an arithmetic that's proving, you can have maybe some pre-computed operations that you know that are valid that are in another state machine. So who's subtracting from the bus is maybe another state machine. So this allows us to be very, very flexible. For example, in the 62 bits, for example, operations that are in 64 bits, they can be proven in a state machine that's a little bit more expensive. If they are 32 bits, maybe they are proven in a 32 bits arithmetic, and so on. Okay. There is also for the memory, for example, in the memory align. So in general, the processor, when it's doing a memory operation, I mean, they send it to the bus and the memory just ends. But the memory is just for memory aligned operations. If it's not memory aligned, maybe we have another intermediate machine that what's doing is solving this non-alignment. So the idea is that, OK, you verify that one is correct, but at the same time, you are assuming that there is two reads maybe that needs to be done. And these are the ones that, these reads alignments, these are the ones that are solved by the memory. A similar trick can be doing, for example, for continuations. The idea is you may have a processor, the state machine of a processor that's executing a code. Okay, so if you want to split that in different chunks, okay, you need some continuation. So the state of the previous one needs to be transferred to the state of the next one. So we do that also with the bus. So we add that we add the state to the bus, and the next state machine they subtracts that to the bus. So this allows us, for example, to do continuations with the bus. So with continuations. There is other interesting tricks is that, so we have two kinds of continuations. These continuations that you do it inside the same proof, okay, that you have these subproofs and you aggregate that to the same proof. But you have also the recursor. The recursor allows you to have different proofs and aggregate them together. Okay, and the trick here is that all these proofs are well packed. So here we have a technique that does not. We don't waste cells inside the prover for these remaining things. So we can connect different proofs and generate them in parallel without memory requirements and connect them together. Okay. So I mentioned a lot of these advantages. I want to mention especially while there is a GPU accelerated, it's really fast. And it's a fully open source, so anybody can build. It's not a system. It's just a code that you can download and you can run it. It's an open source system that you can run on top of that. This is the timings that we are having right now. So at the total, for example, for proving a block, an Ethereum block, we are proving that in real time, in less than 12 seconds. Okay? So, and here you see the parts where we are spending the time. First, we have if we want to prove an execution, we need to execute that. Okay? And because the RISC-V, we need to somehow emulate this RISC-V. And it's not only that, it's not only execution. We need what we call a minimal trace. We need to something else. Okay? So this is the part that's difficult to parallelize. Actually, there are some tricks that we have in the backlog that we can improve that. But currently, it's a single processor, and this processor right now is running at 300 megahertz, more or less. Okay, so this is it's a time that you will have always in there. Okay, then we have the witness computation. Witness computation very much is building all the polynomials. This step is already done in parallel. Okay, so we have different machines. This can be done in absolutely in parallel. The same that the subproof building itself. This is the core part. Okay, so this is where the real proof is generated. These are very much Merkelizations and entities. Okay. It's interesting that these 5 seconds, we can choose what we want. If we choose a small number, that means that the proofs are going to be smaller, and it's going to be much more proofs. Okay, so we probably will need much more servers in order to have this timing. But this architecture allows us to configure how much we want to spend in each of the phases. And of course, if we have smaller pieces, then we pay it in the aggregation. We need to aggregate them together. Here is important, and this is one of the big characteristics, is that right now, we are currently only at 0.15 seconds for doing an aggregation. Okay, so taking 2 proofs and aggregating in a single proof, this is just 150 milliseconds, which is really, really small. Of course, if you have a lot of subproof, for example, you may have 1,000, 2,000 of different subproof that you want to aggregate, you need to multiply that by log n, the number of subproofs that you are doing. So if it's 2,000, then you need to multiply that by 11, okay, so or 12. So this is around 2 seconds. But as you see, altogether is less than 10 seconds, so we can really prove Ethereum blocks in real time. Okay. Backlog, a lot of things. GPU is, at this point, I mean, it's not public yet, but probably next week or in 2 weeks it's going to be already public. I'm very excited on that. And there is a bunch of things in the backlog that can be optimized, and a lot of these numbers can be lowered very much in the upcoming times. Okay? Prove it, test it, check it. It's here. Okay? Any doubts, any things, please contact us. We are happy. We want this to be used not only inside Polygon. We want this to be used for any project that have interest in building zk proofs. That's it. Thank you very much. And if you have any questions, just don't hesitate to talk to me.